I welcome all of you to the class. As far as today's class is concerned, today we are going to discuss the angular momentum in 3 dimensions, and we will certainly try to continue from where we had left our topic in the previous class. In the previous class, we were talking about the angular momentum of a rigid body about any point P, and the expression that we had obtained was angular momentum about any point P was coming out equal to integral of was omega x integral of y square plus z square dm integral of y square plus z square dm minus omega y integral of xy dm and minus omega z integral of xz dm integral xz dm, and this was about I cap. This was about I cap plus quantities we had were minus omega x. Let me write it beneath this. Minus omega x integral of xy dm minus omega x integral xy dm plus omega y integral of x square plus z square dm minus omega z integral of yz dm along j cap, and the last line was plus. We had plus in fact here as well, plus this expression. Then we have the plus minus omega x integral xz dm integral xz dm minus omega y integral of yz dm integral of yz dm plus omega z integral of x square plus y square integral of x square plus y square dm, and this is along k cap. So this is the expression that we had written last time, okay? And this expression was giving us the moment of inertia of a point P of a rigid body, moment of inertia of the rigid body about point P. We are today trying to simplify this expression. I will here draw a line, and we will recall what we had done prior to this class. We also know that we define if we have a rigid body, okay, and this is, say for example, point P, and this point C, let's suppose there is one more point called the center of mass of this rigid body. if this is the x-axis and this is the y-axis, okay, then we know the mass moment of inertia of the rigid body about x-axis, what we have been writing as Ix or Ixx, I sub xxx, is equal to integral of y square dm divided by integral dm. This we know, okay, we are familiar with this moment of inertia terms. We also know the moment of inertia of the rigid body about y-axis, Iyy, is written as integral of x square dm divided by integral of dm. These things are known to us, okay. And we also know from the addition property of this, if we add up Ixx plus Iyy, okay, let me write here. If we write Ixx plus Iyy, if we add up these two terms, if we add up Ixx with Iyy, we will get integral of x square plus y square, x square plus y square dm divided by integral dm, okay. And we know Ixx plus yy is equal to x square plus y square, so this is the x coordinate, this we write as x, this is the y coordinate, okay. So if we draw the line from this point O to this point P, okay, this line will be equal, this line will be equal, the square of this line will be equal r square, let's suppose, equal x square plus y square by the Pythagoras theorem, okay. So it means as far as this x square plus y square is concerned, it is the perpendicular distance of this point when measured from the z-axis, okay. And we have been saying that Ixx plus Iyy gives us Izz, that is the second moment of inertia about the z-axis, okay. So if you look here, we have integral of y square z square dm. So from the definition, y square z square dm will be equal, it will be, we have to name it, okay, we have to see what does this actually represent, okay. So as far as the entire expression is concerned, integral uh, y square z square dm is concerned, that represents the moment of inertia, okay. In the same way, so if you write this as, like you have this expression here, let me write about this, we have integral of like y square plus z square dm, okay. So as far as this expression is concerned, uh, sorry, not, I need to make a little correction here. As far as Iz, it's not in the denominator, you don't have integral dm, sorry. This is moment of inertia, not the coordinate of the centroid, sorry. Let me make this correction. So as far as this as far as this integral y square plus z square is concerned, like here, when you had integral x square plus y square dm, we are saying that this represents the moment of inertia about z axis, okay. Now when we have integral y square plus z square, this represents the moment of inertia about x axis, okay. Like you have x and y here, therefore it's a moment of inertia about z axis. When you have y and z here, it represents the moment of inertia about x axis. So let me write it here and clean these figures. So we can write this as, we can write therefore this as the moment of this equation, we can simply write as, this is omega x, we can write this as omega x. Then we have this entire term, this term, it represents the moment of inertia about x axis. So I will write this as I xx, we'll write this as I xx, fine. Similarly we have then omega y, I will write this as omega y, okay. Now, as far as the second term is concerned, this integral xy is concerned, we are familiar with these terms, integral xy, when we were talking about the product of inertia. When we are talking about the product of inertia, the product of inertia, we are familiar with these terms in the earlier chapters. The product of inertia of a rigid body, okay, the product of inertia of an area. If we have an area, Okay, then the product of inertia about xy axis. Okay, the product of inertia about xy system is defined as integral of xy. This is the product of inertia. Integral xy is equal to integral xy dl. This represents the product of inertia. We represent this as ixy. So in on this pattern, we can write this as, let me make, we can therefore write this as integral of xy dm as far as this integral xy yz dm. This presents the product of inertia about y, sorry, not this, not this one, this one, the top one, this one. This represents the product of inertia I about xy system. I will write this as ixy. Okay, I will call mine's integral xy dm as ixy, therefore I will have a plus here. Okay, to make it simple, while I write here like mine's integral xy dm, we are writing this as, this is ixy. Okay, so we'll get a plus here. Similarly, about this term, we'll write plus omega z, moment angular velocity about z axis. This will be ixz. This is I xz. And entire thing I will write this along. This is the I component. I will write this as I cap. Same is the second term plus. The second term is, this is omega x. We'll directly write it now. Omega x. Then this is ixy, the product of inertia. Ixy plus omega y. This is x square plus z square. This represents the moment of inertia, second moment of inertia about y axis. I will write this as Iyy minus omega z, since I am writing here plus omega z because minus x integral yz dm is I yz. I will write this as jk. Fine. Then the last one will be plus, this is omega x, this terms, this is omega x, this is ixz, this is plus omega y Iyz plus omega z. This is x square plus y square, which represents izz, ij, and this will be along, this is k cap. Okay, so I can still see we had a long equation. Okay, the equations were very much length here. Okay, the expressions were too long, but this entire expression we have condensed in this form. Okay, so if we clean the figure, we can therefore say, the expressions that we have obtained now are like, the entire equation can therefore be written as, we can write this as angular momentum of the rigid body about point P is equal to, we can write this in a vectorial form. Okay, I can write a matrix C like this. The first element I will write as Ixx. The second component I will write as Ixy. The third component will write as Ixz. Okay, then we have Ixy. Then we have Iyy. Then we have Iyz. And the last component will be, the last one is Ixz, Ixz, Iyz, and Izz. I'm writing these moments of inertia terms first in a matrix, and we'll multiply this matrix by one more matrix, by a column matrix having elements omega x, omega y, and omega z. Okay, fine. Or we'll write this as omega x I cap, omega y j cap. Let me put I caps on their sides. We'll multiply them with omega x I cap, omega y j cap, and omega z k cap. Let me see what happens. Okay, okay, uh, fine. Okay, let me not put the caps here. These I caps, j caps, and k caps. Let me see only the magnitudes. So what it will give me? You see, we can write this entire matrix. We can write this matrix. These equations we can write all these equations in the form of this matrix. Okay, so if you just start multiplying them, we know how two matrices are multiplied: r1 c1. Okay, so we have to take the row from this and column from this, so it will be ixx omega x, okay, that's here, plus ixy omega y, that is here, ixz omega z, that is here. Okay, I cap. Then the second one will be r2 c1, that is ixy omega x, that is here, iyy omega y, that is here, plus iyz omega z, that's here. Same about the third column, third row, and the column here. Okay, so if we multiply these two matrices, we'll exactly get these equations back. Now this is the way of writing the angular momentum, and in fact if we don't put a vector over here, then it's okay, because on the right hand side we just have the magnitude. Okay, because we are not multiplying the right hand side with I cap, j cap, or k cap. We don't have the directions on the right hand side, therefore this essentially has to be the magnitude only, the magnitude of the angular momentum of the rigid body about point P. That's okay. Now if you look at this vector, if you look at this matrix that we have, you will very often happen to see this matrix in your mechanics. Sometimes you see this in the form of this matrix. We often happen to see this matrix, okay, in mechanics, sometimes in mechanics of materials, in MOM 2, and in fact sometimes in the fluid mechanics as well. We do happen to see these types of matrices, and this is called a tensor. Okay, this is called a tensor. What tensor is, we'll not introduce here because that's not the question here. This is called a tensor. Okay, we call this as inertia tensor. We call this as an inertia tensor, the moment of inertia tensor. We write the angular momentum of a rigid body is the product of an inertia tensor and the corresponding angular velocity vectors. Now let's suppose we have a rigid body, and the rigid body happens to be let's suppose we have a circular rigid body. We try to understand, as will come up in the problems, we try to understand the motion of the circular rigid body. Okay, as far as a circular rigid body is concerned, if we are analyzing, say for example, this is the center, in fact the center of mass as well. Let's take this to be our x-axis. Okay, let's take this to be our y-axis. Fine, this is our y-axis, this is our x-axis. Okay, and one more axis, let's take, since we are in 2 dimensions. Okay, fine. Now we know, we are already familiar with the product of inertia, ixy. As far as ixy is concerned, the product of inertia is concerned, we are writing this as integral of x, y, dm. And if you recall your chapter 1, we have been saying that the product of inertia of symmetric bodies, product of inertia of a body about an axis of symmetry is 0. We know this very well. The product of inertia of a body about an axis of symmetry is zero. We have already done it, okay, as a theorem. The product of inertia of a body about an axis of symmetry is zero. That is, if the rigid body happens to be a symmetric body, then Ixy is zero, okay? This Ixy is zero, this Ixz is zero, Iyz is zero, Iyz is zero, Ixz is zero, okay? So the only terms that we have for the symmetric bodies will be Ixx. For symmetrical bodies, we'll be having Ixx 0, 0, 0, Iyy, and 0, and 0, 0, and Izz. This is the inertia tensor for symmetric bodies, because for symmetrical bodies, the product of inertia happens to be zero. This all you should always remember. The product of inertia, whether you are measuring about Ixy system or Iyz system or Ixz system for a three-dimensional case, is same as is for a two-dimensional case. Okay, this is always equal to zero. Now, this equation also gives us an insight about two important things. First of all, when we are in three dimensions, trying to understand the rotation of a rigid body or the motion of a rigid body in three dimensions, we should be familiar with the components of the angular velocity about x, y, and z axis. We should be knowing what is the component of angular velocity along x axis, along y axis, along z axis, number one. And we should also be familiar, we should be knowing what is the moment of inertia of the body about x axis, what is the moment of inertia of the body about y axis, what is the product of inertia of the body about xy system, about xz system, about yz system. These things should be quite known to us, so that we obtain the equation, we find the angular momentum of this rigid body, number one. So these are two things. We should be knowing the angular velocity vector, and we should be knowing the inertia tensor to find the angular momentum. Okay, these two things are very important for us. Now the question is, if we are trying to understand the kinetics of a rigid body, essentially we are trying to find the velocity of a rigid body in three dimensions, acceleration of a rigid body in three dimensions, or we are trying to find out other parameters of the rigid body in three dimensions. Now the question is, why we are focusing our attention on the angular momentum? Why, what is associated with this angular momentum that we have laid this as a basis for understanding the kinetics of rigid bodies in three dimensions? Okay, why does the kinetics of rigid bodies in three dimensions start from the angular momentum concept? Why we are familiarized with this concept of this version of this angular momentum, okay, to understand the kinetics of the rigid body? This is a very fascinating question and a very important question, in fact, because the answer to this question is that it is this angular momentum equation, that's in front of us, that will give us the equations of motion of a rigid body in three dimensions, number one. So it means we are narrowed down from a wide concept of understanding the moment of inertia in terms of an inertia tensor, okay, to understanding the equations of motion of a rigid body in three dimensions. That is, it becomes very important for us to derive, or okay, or to understand, or to or to formulate the equations of motion of a rigid body from this citrus, from this inertia tensor. I mean to say, from these equations, from this angular momentum equation, let's try to evaluate the equations of motion of a rigid body in three dimensions. Okay, and evaluation or finding out or derivation of the equations of motion of a rigid body from this formula is very important, as was done by an earlier mathematician in the 19th century by Euler. Okay, Eulerian concepts. Euler did it using this strategy of finding the equations of motion of a rigid body. So we are left with two important things. That is, first of all, finding out the equations of motion of a rigid body using these equations. I mean to say, using these equations in front of us, using this matrix multiplication equations, or using these equations in terms of inertia tensor, or using the equation of this angular momentum to find out the equations of motion of a rigid body. And then, second, very important, applying the equations of motion of the rigid body on the physical systems, on the engineering systems, to obtain their velocities, angular acceleration, linear acceleration, force, impulse, momentum, so on and so forth. So now what the strategy has been laid is that after finding the angular momentum in terms of this inertia tensor, now we have to do something else. That is, from here, let's try to find out the equations of motion of a rigid body in three dimensions. That I will be doing in a while from now, but after taking a few questions from you.